Hi everyone, Mrs. Besega here, and today we're going to work on vector components. A vector component is the part of the force that pushes up or down. And the big idea of this video is that your x and y components of a vector can be resolved or broken into more useful parts than the total. Now, let's say I take a vector that lies along this grid, and each box on this grid equals 1 Newton by 1 Newton. Well, then this vector, the total vector that I'm drawing in purple, would be the hypotenuse of a right triangle. The y component would be 2 newtons down, so 2 boxes down. And the x component, or how hard this force is pushing to the right, would be 1, 2, 3 boxes or 3 newtons right. The x and y components show us how much force is going down and right. Now, it's not likely that you're going to get a problem that has a grid with Newton-sized squares on it. So let's do an application. Let's say I have a person pulling a really heavy box, and they put an applied force of 10 newtons to the right at 30 degrees above the horizontal. The ground supports it with normal. There's some friction here, and we know there's a weight associated with this box of 12 newtons. We want to find the normal force, and we know that the applied force is kind of funny there. See how the applied force is the only one that's not perpendicular to its buddies? The applied force is what we're going to break into its components. We want to find the x component, how far this force pushes to the right, and the y component, how much this force pushes upward. Notice this is the sides of the right triangle. That means I can use trigonometry, sine, cosine, and tangent to find the x and y components. Because it's the opposite and adjacent sides to 30, I know the function I want to deal with is sine or cosine. Okay, so let's say my 10 Newton force is the hypotenuse and I know 30 degrees, and we're just going to try sine and cosine and see which one fits. Remember that cosine is the adjacent side over the hypotenuse. But hey, in this case, the adjacent side, well, that's the x component. And the hypotenuse is FA, the total force. So we're going to say the x component is going to go with cosine. And as long as you choose theta, or the angle, to always be from the horizontal, you'll always be able to use this equation here. Fx is equal to f cosine theta, where f is the value on the hypotenuse, theta is the angle from the horizontal. In this case, f cosine 30 degrees, or 10 cosine 30, gives me 8.7 newtons to the right. In the y direction, the y component must go with sine then. If cosine went with x, then sine must go with y. Because sine is opposite over hypotenuse, and the y component is the opposite side of this triangle. So taking sine is equal to FAY over F, and rearranging, I see that Fy is equal to F sine theta, where F is the hypotenuse and theta is the angle from the horizontal. I drew these in corresponding colors, so blue always goes with Y, red always goes with X, and purple represents the hypotenuse. Substituting in, that's 10 sine 30 is 5 newtons up. So what are we going to do with this information? We're going to take our x and y components as calculated here and simply redraw them onto the existing free body diagram. Now the trick with this, draw your free body diagram with all the other vectors exactly the same as before. So friction was 4 to the left, normal was unknown, gravity was 12. But now, instead of drawing that up into the right diagonal vector, I'm going to draw the y component as 5 newtons up, and the x component was, 8.6 something newtons to the right, 8.7 newtons to the right. And now we can solve. In the x direction, I can see that the net force is 8.7 newtons to the right minus 4 newtons to the left. This object is accelerating to the right. It has a net force of 4.7 newtons to the right, so it is not in equilibrium. But let's say that in the y direction, it probably should be in equilibrium. If I'm pulling a box to the right, it shouldn't be sinking into the ground or floating up into the air. The normal force plus the y component, the 5 newtons Fay, should equal the 12 newtons of gravity pulling down. That means in the y direction, because it's in equilibrium, that normal plus 5 equals 12 newtons of gravity pulling down. Subtracting the 5 to the other side means the normal force is 7 newtons up. So let's recap this problem all the way from the beginning. In the beginning, we were given an original free body diagram, and we identified that the 10 Newton applied force was the one that just didn't fit in with the others. It was off at an angle, so we wanted to use our component skill to break that, resolve it into its components, so it was easier to use. We used the cosine and sine, cosine with x and sine with y, to calculate the x and y components. And finally, we redrew the free body diagram, substituting in our components for x and y in place of the original applied force. This makes it easier to do problems because now everything is already perpendicular to each other. In your next homework assignment, the rest of the problems will be like this. Best of luck!